this video, we are going to conclude our discussion on section 5.1, exponents and logarithms. In particular, we will look at the two objectives today of creating some of these properties of exponential and logarithmic functions. And we'll also use this power rule and see how it is massively important, massively useful for our work with solving equations. And so let's start here. The first line, we have a rule written in exponential form. And in the previous video, we saw how we would write this in logarithmic form. So c equals 10 to the d. How does that look in logarithmic form? We know that because it's base 10, it'll be a logarithm. We also know that the logarithm equals the exponent. And so the exponent of d goes on the right-hand side. And so we have log of c equals d. Moving ahead to the second line. How do we handle the p component on the left? 10 to the c multiplied by 10 to the d. Well, how do you handle when you multiply? Add the exponents. The logarithmic rule for this, remember, because logarithms are just a different way of stating the exact same thing, this one would look like if we're taking the logarithm of a product of numbers that has the result of adding the logarithm. Please notice the format that we have. On the left-hand side, we're saying we're multiplying the exponents, or rather we're multiplying the powers with a shortcut of adding the exponents. In logarithmic form, this is how that same piece is stated. If you are multiplying bases, the shortcut is to add the exponents. Continuing to the third line. How did we handle a quotient? We had the shortcut of subtracting. Well, it's no different when we have our logarithms. If we have a quotient, the shortcut is the same. You subtract. So it is the log of c subtract the log of d. Progressing to the fourth line, a power raised to a power. What was the rule? We had to multiply the exponents. It's the same thing here. If we are taking the logarithm of a power, the rule is to turn it into multiplication. And that's done with d multiplied by the logarithm of c. And thus we have the primary logarithmic rules we will use throughout today. All right, expand these pieces. Please notice that 12x is saying 12 times x. And since that is multiplication, we know that it will split up into addition. And we're done. Noting the same principles apply to the second problem. X multiplied by the quantity x plus 4. Because we're taking the logarithm of a product, our rule tells us that will get split up into two logarithms based on addition. Continuing with example number 8, we'll notice, of course, that our logarithm is not a product. Instead, we're taking the logarithm of a quotient. And we saw before with our exponents, if we have a quotient, the shortcut is subtraction. So, with a quotient, our rule is to split it up with subtraction. We're done.
Does it matter? What if you go log 5?
And the second part has the exact same thing. Noting that we have a quotient may be split up using subtraction. I'd like you to look at what I just wrote and consider why this may be confusing. At the back part, log of x plus 2, consider the order and operations. Do I intend for this to be a log, then addition?
So we gotta put the x plus 2.
Or is it intended to be addition, then log?
You put log and then parentheses.
Yeah. We should have this as x plus 2 first, then take the logarithm, which is, of course, why we were using the set of parentheses here. Our third exponent rule, our third logarithmic rule, had to deal with a power to a power. And what we noted, when we have an exponent, we can bring the exponent down and turn it into multiplying.
Why wouldn't it be the log?
To continue this particular thing, Alex made the point that if we were doing what we had with the last video, the log and the 10 would cancel and we'd have just the number 3. Well, we encounter the same thing. Log of 10 basically cancels because it's actually just the number 1, and we're left with just 3 to fully simplify it. Well, I was not planning on fully simplifying these. This particular example was picked just so that we could run through and see how the rules work. Let's look at our next one. With an exponent of 3.2, we can bring down 3 2/10, and that will be multiplied by the remaining logarithm. No matter what the exponent is, the exponent gets brought down with multiplication. So with a variable of x, we'll bring it down and multiply by the logarithm. Likewise, it doesn't matter if the base is a variable. Whatever the exponent is, the exponent comes down and we will multiply by the logarithm. One piece you must be careful about, however, and this is a very, very common error. Many students will look at the next example, see the exponent of 4, and bring it down and say this is the log of 5x. No, that is wrong. Because that exponent of 4 was not on the 5. It was on only the x. So to correct this type of a mistake, we cannot apply the exponent rule unless it's a single power. Instead, we would have to do this in 2 stages. The first stage is to split up the multiplication, 5 times x to the 4th, and have 2 separate logarithms.
Wow.
After splitting up the 2 logarithms, then it's acceptable to apply this power rule, giving us logarithm of 5 plus 4 times the logarithm of x. Similarly, we will encounter the same problem with this last one. focusing entirely on variables, we would still need to recognize this is b times, or c times b to the x power. Well, because there is a product, the product needs to be split via addition. Continuing that further, the power then, log of b to the x, can likewise be split as x times the log of b. Final word of caution, considering order and operations, please be aware that log of x to the fourth is not the same thing as log of x quantity to the fourth. Those are not the same thing. You cannot treat them as equivalent. Finally, let's start applying those rules. We have multiplying rule, we have a product rule, we have a quotient rule, we have a power rule. Let's use them to actually start solving some equations. What do? Well, our standard rule is power rule, because we could take a logarithm of both sides. When we take a logarithm of both sides, we've now created something which will fit. The switching back and forth between purple and gold is kind of weird. After taking the logarithm, we should recognize this is perfectly set up to apply that power rule. 2 to the x power. Applying the power rule, we'll have x multiplied by the logarithm of 2 equals the logarithm of 30. And now what would you have to do to get x by itself? What would you have to do to get rid of this multiplication? So we'll divide by the log of 2. And we now have something that we'd be able to put into our calculators. X equals the log of 30 divided by the log of 2. Please do not think that this is equal to the log of 15. That is not true. This is not the log of 15. There is absolutely no shortcut rule for a logarithm divided by a logarithm. However, we can put both of these into our calculator and see the results. Alright, typing in log of 30 divided by the log of 2. Of course, we know the logarithm button is over here. So the logarithm of 30 divided by the logarithm of 2. And so we obtain our answer to 3 significant digits. X is equal to 4.91. And I do want to verify that this is not the same thing as log of 15. So let's go back and just quick numerically show the logarithm of 15, not the same thing. There is no shortcut for logarithm divided by logarithm. Don't think that you can do it that way. It does not work. All right, let's consider this problem now. You notice how we have a single occurrence of x? This is a piece that actually does fit inverse reverse. So we could set up a function loop diagram, going back to chapter 2. We could set up a function loop diagram and just work backwards through it. Well, let's consider our options then. In order to get the x isolated, what would we have to move over? Well, one thing we can get rid of is this multiply by 2,000. So we'll divide by 2,000. Giving us 1.07 to the x is equal to, and what's 4,200 divided by 2,000?
2.1. Good enough.
I don't know.
All right, so now what?
So we
Now we will have to take the logarithm. By taking the logarithm of both sides, we have set something up to take advantage of the power rule. You noting how incredibly useful this power rule is for us?
Hate math.
By applying the power rule, this becomes x multiplied by the log of 1.07 equals the logarithm of 2.1. To finish it off, we'll simply divide. X is equal to the logarithm of 2.1 divided by the logarithm of 1.07. And we'll now enter that into our calculators. 10.9 is what you're giving me, Alex? Alright. 10.97. Okay, if it were 10.97, the 7 will tell us to round up. So to 3 significant digits, that's 11.0. To 3 significant digits. So let me write that up then.
shut up.
Alright, solve this problem. Well, a lot of times students will look at this and say, okay, we've got an exponent, so let's take a logarithm. Okay? If we were to take this logarithm then, we could bring down the exponent, so we'd have 4 times the logarithm of 1 plus r equals the logarithm of 2.8. At this point, I want to ask you, why in the world are we doing it this way?
Because you wanted to? Like in your class?
Because you said a
No.
million people do it first.
No, what I said, sometimes students will look at the problem and see an exponent and then instantly assume, since it's an exponent, I need a logarithm. This one shows that that's not true. Taking a logarithm as our first step here, our variable is now trapped inside a logarithm, giving us a whole bunch of stuff that would be difficult to get around. We would have to get rid of the logarithm. We'd have to get rid of times 4. We'd have to get rid of subtracting 1. Taking a logarithm creates a lot of extra work. We don't want to take a logarithm on this problem because of the location of the variable. Remember, logarithms were created with the goal of finding out what the exponent is. The end answer, the thing you're looking for, should be in the exponent if we're using logarithms. Our variable here is not in an exponent, so using a logarithm is not the correct strategy. We've already done problems like these. We can get rid of the exponent by taking the 1/4 power. And then when we subtract 1, we have the 4th root of 2.8 minus 1. We've got something we can put into our calculator directly. We don't need logarithms. Make sure you pay attention to the location of the variable. If the variable is inside the base, you're working with exponential functions, and you don't need logarithms. If the variable is in the exponent, that's when you need logarithms. Consider now our example 13. Where is the variable? Is the variable in a base, or is the variable in an exponent? Because the variable is in the exponent, we need logarithms. So tell me what we need to do.
Well, what you're gonna do is, that's 7.
Okay, dividing by 7, as Ryan told us, gives us 2 to the 5 over d equals 16 over 7. Then what?
Then you could take the log.
Our next step is to take the logarithm. And the reason we want to take the logarithm is to take advantage of this power rule. By taking a logarithm and applying the power rule, we can get rid of exponents entirely. And now what? Well, there are a lot of different ways that we can solve this particular problem. To me, the easiest is to recognize we have divide by d. If I divide by the 5, or if I divide by the logarithm of 2, I still have the problem that I'm left with 1 over d. I'd rather have something of the form d equals blah, because of course that's what we're trying to get. So instead of doing stuff with the 5 or the logarithm of 2, I am instead going to choose to multiply both sides by my variable. To me, algebraically, this seems like it's the simplest thing. Which gives me then 5 times the logarithm of 2 equals d multiplied by the logarithm of 16 over 7. Which seems pretty easy to solve now. To isolate our variable, we'll divide. And so we have something that we can put into our calculator. Five times the logarithm of 2 divided by the logarithm of 16 over 7. Giving us 4.19. E is equal to 4.19, rounding to 3 significant digits. All right. Looking at the problem, inverse reverse has failed. So what are we going to do? Or rather, inverse reverse is not immediately available. Could we somehow manipulate this algebraically to go from having 2 occurrences of x down to 1? We're actually going to solve this problem 2 times, using 2 separate strategies. They're both built on the idea of getting a variable by itself. The first method I'm going to employ is to just start by taking logarithms. If we take a logarithm right away of both sides, we would have the log of 1.06 to the x equals the log of 0.9 times 1.09 to the x. Please notice, because of the product, we can split that up. We know that when we have a product inside a logarithm, we can actually separate it as a sum of 2 logarithms. From here, we should recognize powers. If the exponent of x is two locations, we can apply the power rule to both of them. X times the logarithm of 1.06 equals the logarithm of 0.9 plus the logarithm x times the logarithm of 1.0. Well, now what? Ultimately, keep in mind our goal. X equals blob. Well, if we're going to go after x equals blob, we need to put all of our variables on one side of the equation, all the non-variables on the other. So I'm going to subtract off this piece from both sides. By subtracting it, we'd recognize that we have x times the log of 1.09 minus x times the log of 1.06 equals the logarithm of 0.9. To progress further, what can we do with this thing? You notice how they both have a factor of x?
Take out the x.
Factor out the x. Leaving behind a pair of logarithms. Well, we have x times blob equals logarithm of 0.9. Yeah, we'll just divide by the blob. The logarithm of 0.9 all over this blob. And we now have something that we can type into our calculator. So we had the logarithm of 0.9 parentheses divided by, remember that since we're dividing by a blob, we want to have a set of parentheses for the blob. The logarithm of 1.09 minus the logarithm of 1.06, and don't forget to write parentheses to close up the blob. Here's our result, negative 3.78. Assuming that we've typed everything up correctly and we haven't made any mistakes, we have a solution. Huzzah.
Yay.
I will let you know, there's no way in the world I would do the problem this way. This is the harder way to do it.
It'll show us the
This is a lot of algebra, right?
You are
We can solve this. This is taking advantage of a lot of the logarithmic rules. It's a completely valid strategy. It's not the one that I would employ. I would like a faster way to get those x's combined. And here's the way I see it. If I divide right off the bat, when we divide straight off the bat, you notice that the exponents are the same.
I was thinking.
Well, because the exponents are the same, we could take advantage of our exponent rule and leave this as just 1x. And this is a whole lot easier then. At this stage, I can take my logarithm and And having taken the logarithm, we can apply the power rule one time instead of two. X multiplied by the logarithm of and finally, to isolate the x by itself, get rid of the multiplication, divide. And now we have something that we can put into our calculators. The logarithm of 0.9 over the logarithm for this quantity, 1.06 over 1.09. So, a logarithm of, I forgot the order of it, 0.9. 0.9 divided by the logarithm of 1.06 divided by 1.09. So why aren't they matching? One's positive, one's negative. What went wrong? Well, when we did it the first way, at this point we had the logarithm of 1.06 subtract the logarithm of 1.09. Well, at the next stage, we had the logarithm of 1.09 subtract the logarithm of 1.06. Basically, you screwed up. I switched around the order of subtraction. Obviously, you're not allowed doing that, so that error followed it with way downward and caused the rest of it to basically make a mistake.
What was the end answer
And
there?
of course,
Positive.
the end answer then, the correct end answer, the three significant digits was 3.78. And right away in class, people started commenting, man, that second one's so much easier. Yeah, I agree. However, both of them still show the power of this rule. This power rule is massively, massively important to working with logarithms. In fact, we'll use it for virtually everything when we need to solve a logarithmic problem.